Welcome to Lecture 2.1, AI versus ML versus Deep Learning versus Generative AI. This is our first deep dive into the actual exam content, and we're starting with the most fundamental concepts you need to know. This lecture maps to Domain 1.0, Objective 1.1, compare and contrast various AI types and techniques used in cybersecurity. Domain 1 accounts for 17% of the exam, and understanding these foundational concepts is essential because they underpin everything else in the course. By the end of this lecture, you'll be able to clearly distinguish between AI, machine learning, deep learning, and generative AI, understand how they relate to each other in a hierarchy, and most importantly, know how each one applies specifically to cybersecurity. Let's get started. This is the most important visual to internalize for the exam. Think of AI as a series of nested boxes, where each inner box represents a more specialized subset of the outer one. At the broadest level, we have artificial intelligence. AI encompasses any system designed to mimic human cognitive functions, like reasoning, learning, problem-solving, and decision-making. This includes everything from simple rule-based expert systems to the most advanced neural networks. Inside AI sits machine learning. ML is a subset of AI, where systems learn patterns from data, rather than being explicitly programmed with rules. Instead of writing if this, then that rules, you feed the system data, and it discovers the patterns itself. Inside ML, we have deep learning. DL uses neural networks with multiple layers. That's where the deep comes from, to automatically extract increasingly complex features from raw data. While traditional ML often requires handcrafted features, deep learning learns the features themselves. And at the innermost level, we have generative AI. Gen AI is a subset of deep learning that can create new content, text, images, code, audio, rather than just classifying or predicting from existing data. Here's the key exam insight. Understand that these form a hierarchy, and each layer adds capability to cybersecurity. AI gives us rule-based detection. ML adds pattern recognition, DL enables complex feature extraction from raw data, and Gen AI introduces content generation capabilities for both attack and defense. Let's start at the top of the hierarchy, with artificial intelligence itself. AI is defined as the simulation of human intelligence by computer systems. It encompasses any technique that enables machines to mimic cognitive functions like learning, reasoning, problem-solving, perception, and language understanding. That's a broad definition, and it's intentionally broad. For the exam, you need to know two categories of AI. First, narrow AI, also called weak AI. This is AI designed for a specific task. And here's the crucial point. All current AI systems, including ChatGPT, fall into this category. Every spam filter, every malware classifier, every facial recognition system, they're all narrow AI. They excel at their specific task, but can't transfer that knowledge to a different domain. Second, general AI, also called strong AI. This is a hypothetical AI that would have human-level reasoning across all domains. It's an important concept to understand for the exam, but know that it does not exist yet. It's purely theoretical. Now, how does AI apply to cybersecurity? Traditional AI in security includes rule-based intrusion detection systems like SNORT, where you write specific signatures to detect known attacks. Expert systems that help make security policy decisions based on predefined rules. Automated vulnerability scanning tools. And security orchestration, automation and response platforms, SOAR, that automate incident response workflows based on predefined playbooks. These are foundational, and while they've served us well, they have a major limitation. They can only detect what they've been explicitly told to look for. That's where machine learning comes in, which we'll cover next. Now let's move into machine learning, the first major subset of AI. ML refers to algorithms that learn patterns from data without being explicitly programmed. Instead of writing rules, you feed the system training data, and it discovers the patterns itself. The system then improves its performance through experience. For the SecAI Plus exam, you must understand 3 megaliters paradigms. First, supervised learning. This is when you train the model with labeled data. You give it inputs along with the correct outputs, and it learns to map between them. Think of it as learning with an answer key. In cybersecurity, supervised learning powers malware classification. This file is malware or benign. Spam detection. This email is spam or not. And phishing URL identification. This URL is legitimate or phishing. Second, unsupervised learning. Here, the model works with unlabeled data and must find hidden patterns on its own. There's no answer key. This is incredibly valuable for security because it can find things you didn't know to look for. Use cases include anomaly detection, finding unusual patterns in network traffic that could indicate a breach, clustering similar network behaviors to identify groups of compromised machines, and grouping user behaviors to spot insider threats. Third, reinforcement learning. This paradigm learns through trial and error. The system takes actions, receives rewards or penalties, and adjusts its strategy. In security, this applies to adaptive security policies that adjust to changing threat landscapes, automated penetration testing where the system learns the most effective attack paths, and dynamic firewall rules that adapt based on observed attack patterns. The exam may present scenarios where you need to identify which learning paradigm is best suited for a particular security task. The key distinction is, labeled data means supervised, unlabeled pattern discovery means unsupervised, and learning through actions and rewards means reinforcement. Now we go deeper, pun intended, into deep learning. DL uses neural networks with multiple hidden layers that automatically extract hierarchical features from raw data. The deep in deep learning refers to the depth of these layers. Look at the layer diagram on the left. Data flows from the input layer, through multiple hidden layers, to the output layer. Each hidden layer extracts increasingly abstract features. For example, in malware analysis, the input layer might receive raw byte sequences. The first hidden layer identifies low-level patterns like specific byte combinations. The next layer recognizes higher-level sequences, and deeper layers identify behavioral patterns that indicate malicious intent. The output layer then makes the final prediction, threat or benign. For the exam, you need to know 3 key DL architectures. First, convolutional neural networks, or CNNs. These excel at processing grid-like data, especially images. In security, CNNs are used for image-based malware analysis, where malware binaries are converted to visual representations, visual CAPTCHA solving, and network traffic visualization. Second, recurrent neural networks, or RNNs. These process sequential data, where order matters. They're used for analyzing log sequences, detecting patterns in network traffic flows, and any time series security data. Third, transformers. This is the architecture behind GPT, BERT, and most modern language models. The key innovation is the attention mechanism, which allows the model to focus on the most relevant parts of the input. In security, transformers power NLP for threat intelligence analysis, code review and vulnerability detection, and log summarization. Here's the critical exam distinction between ML and DL. Traditional ML requires you to manually engineer features. You decide what characteristics the model should look at. Deep learning automatically extracts features from raw data. This is a fundamental difference that CompTIA loves to test. Generative AI is the innermost and newest layer of our hierarchy, and it's arguably the most transformative for cybersecurity, both as a powerful defensive tool and as a dangerous threat vector. Gen AI creates new content by learning patterns from training data. It doesn't just classify or predict, it generates. On the defense side, Gen AI is revolutionizing security operations. It can automatically generate security reports and documentation, saving analysts hours of manual writing. It can perform automated code review and detect vulnerabilities by understanding code semantics, not just pattern matching. It excels at summarizing threat intelligence reports, taking hundreds of pages and extracting the key indicators and recommendations. It can generate synthetic data for training security models when real attack data is scarce. It can create incident response playbooks from natural language descriptions. And through ChatOps interfaces, it enables analysts to query security data using plain English. But here's the flip side, and this is heavily tested on the SecAI Plus exam. Gen AI is also a powerful weapon for attackers. Automated phishing. Attackers use LLMs to generate highly convincing, personalized phishing emails at scale, with perfect grammar and contextual awareness. Deepfake creation enables impersonation of executives for voice and video-based social engineering. Polymorphic malware that automatically modifies its code to evade detection. Social engineering at unprecedented scale, with each message tailored to the target. Automated discovery and exploitation of vulnerabilities. And misinformation campaigns that generate convincing but false content. This dual-use nature of Gen AI is a core theme of the SecAI Plus exam. You need to understand both how to leverage Gen AI for defense and how to defend against Gen AI-powered attacks. We'll go much deeper into this in Domain 2 and Domain 3. This comparison table is your quick reference for the exam. Let me walk through the key differentiators row by row. Definition row. AI is the broadest, any system mimicking human cognition. ML narrows it to algorithms that learn from data. DL further narrows to multi-layer neural networks. Gen AI specifically creates new content. Data needs. Traditional A. I can work with rules and knowledge bases. You don't necessarily need data, just expertise to write rules. ML needs moderate amounts of structured, labeled data. DL is hungry for large volumes of raw data. And Gen AI requires massive datasets to learn the distributions it needs to generate from. Feature engineering. This is a critical exam distinction. Traditional AI uses handcrafted rules. ML uses hand-engineered features. A human decides what attributes the model should consider. DL automatically extracts features. No human feature engineering needed. Gen AI goes further and learns the entire generative distribution of the data. Security use cases. AI powers rule-based IDS and SOAR playbooks. ML enables malware classification and anomaly detection. DL handles advanced threat detection and network traffic analysis. Gen AI supports threat intelligence analysis, automated code review, and phishing defense. And critically, the threat vector row. AI systems can be evaded by crafting inputs that don't match rules. ML systems face adversarial ML attacks and data poisoning. DL models are vulnerable to model inversion and model theft. Gen AI enables deepfakes, automated phishing, and polymorphic malware. The exam tip at the bottom is essential. The CY0-001 Plus exam consistently tests the dual-use nature of every AI technology. For every defensive application, there's an offensive counterpart. Make sure you know both sides. Let's map these AI technologies to the security operations lifecycle, because this is how the exam contextualizes them. The security lifecycle has 4 main stages. First, prevention, where AI-powered vulnerability scanning uses rule-based checks. ML provides predictive risk scoring to prioritize what to patch first, and Gen AI assists with automated code analysis and threat modeling documentation. Second, detection. This is where ML really shines. Supervised ML classifies known threats, while unsupervised ML identifies anomalies that could indicate unknown attacks. Deep learning powers advanced network traffic analysis and user entity behavior analytics, or UEBA, which builds behavioral baselines for users and entities and flags deviations. Third, analysis. When a potential threat is detected, Gen AI summarizes threat intelligence reports and correlates indicators of compromise. ML helps with automated alert correlation, reducing alert fatigue. And DL extracts features from complex, unstructured data like malware samples or network captures. Fourth, response. AI orchestrates SOAR playbooks to automate response actions. Gen AI generates incident reports and executive summaries, and ML helps prioritize incidents so analysts focus on what matters most. The key insight for the exam: no single AI technology handles the entire lifecycle. Real-world security operations use all of these technologies together, each playing to its strengths at different stages. CompTIA may test your understanding of which technology is most appropriate for a given stage or task. Let's consolidate everything with key takeaways and exam question patterns. 5 things you must remember. 1. AI, ML, DL, and Gen AI form a hierarchy. Each is a subset of the one above it. 2. ML learns from data without explicit programming. And you must know all 3 paradigms: supervised for labeled data, unsupervised for finding hidden patterns, and reinforcement for learning through trial and error. 3. DL automatically extracts features through neural network layers, and you should know the 3 main architectures: CNNs for images and grid data, RNNs for sequences, and transformers for NLP and attention-based processing. 4. Gen AI creates new content and is both a powerful defensive tool and a dangerous threat vector. 5. Every AI type has both defensive applications and offensive threat implications, the dual-use principle. Now let me show you common exam question patterns. If the exam asks about detecting unknown threats in network traffic, think unsupervised ML and anomaly detection. Because the threats are unknown, you can't use supervised learning. If asked what distinguishes DL from ML, the answer is automatic feature extraction. If asked about generating phishing at scale, that's generative AI and LLMs. And if the scenario involves classifying malware into known families, that's supervised ML classification because you have labeled categories. Practice identifying the AI type from the scenario description. The exam rarely asks, "What is ML?" directly. Instead, it describes a security scenario and asks which technology or approach is most appropriate. That wraps up Lecture 2.1. In the next lecture, we'll dive deeper into ML paradigms and their specific security applications. Outstanding work completing Lecture 2.1. Let's recap what you've mastered. You can now clearly distinguish between AI, ML, deep learning, and generative AI. You understand that they form a hierarchy where each is a subset of the one above it. You can map each technology to specific cybersecurity use cases across the security operations lifecycle. You understand the dual-use nature, both how these technologies defend and how they can be weaponized. And you can recognize common exam question patterns for Objective 1.1. Coming up next in Lecture 2.2, we'll take a much deeper dive into the 3 machine learning paradigms: supervised, unsupervised, and reinforcement learning. We'll look at specific algorithms within each paradigm, detailed security use cases, and how to choose the right paradigm for a given security scenario. Great job, and I'll see you in the next lecture. Welcome to Lecture 2.2 Machine Learning Paradigms. In the previous lecture, we established that machine learning is a subset of AI, where algorithms learn patterns from data. Now we're going to take a deep dive into the 3 major ML paradigms that you'll encounter on the SecAI Plus exam: supervised learning, unsupervised learning, and reinforcement learning. This is critical material, because the exam will present security scenarios and expect you to identify which ML paradigm is most appropriate. Understanding the strengths, limitations, and specific security applications of each paradigm is essential for both the exam and real-world AI security work. By the end of this lecture, you'll be able to explain how each paradigm works, identify the right paradigm for a given security scenario, name specific algorithms within each paradigm, and understand the security implications and vulnerabilities of each approach. Let's get into it. Let's start with a bird's-eye view of all three paradigms before diving deep into each one. Supervised learning is like learning with a teacher. You provide the algorithm with labeled training data, inputs paired with their correct outputs, and it learns to predict the output for new, unseen inputs. This is the most commonly used paradigm in security applications because we often have labeled datasets of known malware, known phishing emails, and known attack signatures. Unsupervised learning is like exploring data on your own without a teacher. The algorithm receives unlabeled data and must discover hidden patterns, structures, or groupings by itself. This is particularly valuable for security because it can detect unknown threats that haven't been seen before, things that wouldn't match any labeled training data. Reinforcement learning is like learning to play a game. An agent takes actions in an environment, receives rewards for good actions and penalties for bad ones, and gradually learns an optimal strategy. This is an emerging paradigm in adaptive security, where systems need to continuously adapt to changing environments. Keep these analogies in mind. The exam often describes scenarios that align with one of these paradigms, and you'll need to quickly identify which one fits. Let's dive deep into supervised learning. The fundamental formula is: input plus label produces a trained model, which then makes predictions on new data. The model learns the mapping between features and known outcomes. Supervised learning has two main task types that you need to know for the exam. First, classification, assigning inputs to discrete categories. This is the most common in security. Examples include malware classification, where the model decides if a file is malicious or benign. Phishing detection, determining if an email is phishing or legitimate. Network traffic classification, flagging normal versus malicious traffic. And spam filtering. The key algorithms for classification include random forest, which builds multiple decision trees and votes, support vector machines or SVMs, which find the optimal boundary between classes, logistic regression, which despite its name is a classification algorithm, naive Bayes, which is fast and effective for text classification, and decision trees, which are interpretable and easy to understand. Second, regression, predicting a continuous numeric value. In security, this includes risk scoring, where you assign a numeric risk score from 0 to 100 to a vulnerability, predicting the time to breach detection, estimating the financial impact of a security incident, and calculating the probability that a detected threat is a true positive. Key algorithms include linear regression, ridge and lasso regularized regression, gradient boosting methods like XGBoost, and neural networks for complex relationships. The exam may present a scenario and ask which type of supervised learning task it represents. Remember, if the answer is a category, it's classification. If it's a number, it's regression. Now let's walk through the supervised learning workflow as it applies to security, because the exam tests your understanding of this end-to-end process. Step 1. Collect labeled data. You need labeled samples, malware and benign files, phishing and legitimate emails, attack and normal network traffic. The quality and quantity of your labels directly determine model performance. In security, labeling is often the hardest part, because it requires expert analysis. Step 2. Feature engineering. You extract relevant attributes from the raw data. For malware analysis, features might include file size, API calls, imported libraries, byte patterns, and entropy. For email classification, you'd extract header fields, sender reputation, URL characteristics, and text features. This is where domain expertise matters, knowing which features are discriminative. Step 3. Train the model. Feed the features and labels into your chosen algorithm. The model learns decision boundaries that separate the classes. This involves splitting data into training and validation sets, tuning hyperparameters, and iterating until performance is satisfactory. Step 4. Validate and test. Evaluate on held-out test data that the model has never seen. This is where the 4 key metrics come in, and these are exam testable. Accuracy is the overall percentage of correct predictions, but it can be misleading with imbalanced data. If 99% of traffic is normal, a model that always says normal has 99% accuracy but catches 0 attacks. Precision tells you of all the things you flagged as threats, what percentage were actually threats. High precision means fewer false alarms. Recall tells you of all actual threats, what percentage you caught. High recall means fewer missed threats. F1 score is the harmonic mean that balances both. Step 5. Deploy and monitor. Deploy to production, but the work isn't done. You must monitor for model drift, when the model's performance degrades, because the real-world data distribution changes. As new threats emerge, you'll need to retrain with updated data. Now let's explore unsupervised learning. The key characteristic: no labels are required. The algorithm discovers hidden structures, patterns, and groupings in data on its own. This is incredibly powerful for security, because attackers constantly create new methods, and unsupervised learning can detect novel attacks that supervised models trained on known threats would miss. There are three main techniques within unsupervised learning. First, clustering, grouping similar data points together without predefined categories. In security, you might cluster network flows by behavior, to spot command and control traffic that clusters differently from normal browsing. Or cluster users by their activity patterns to identify groups with suspicious behaviors. Or identify new malware families by clustering samples with similar characteristics. Key algorithms include k-means, which partitions data into k-clusters, DBSCAN, which can find arbitrarily shaped clusters and is great at identifying outliers, and hierarchical clustering, which builds a tree of clusters. Second, anomaly detection. This is arguably the most valuable unsupervised technique for security. It identifies data points that deviate significantly from what's considered normal. Use cases include detecting unusual login patterns like a user suddenly logging in from a new country at 3 a.m., flagging abnormal data exfiltration volumes, and identifying behavior consistent with zero-day exploits that don't match any known signature. Algorithms include isolation forest, which isolates anomalies by randomly partitioning data, one-class SVM, which learns the boundary of normal data, autoencoders, which learn to reconstruct normal data and flag high reconstruction error inputs as anomalies, and local outlier factor. Third, dimensionality reduction, reducing the number of features while preserving important information. While this sounds less exciting, it's crucial for visualizing high-dimensional security data, compressing features for faster real-time processing, and removing noise. PCA, TSNE, and UMAP are the key algorithms. For the exam, the critical connection is, whenever a question mentions detecting unknown threats, novel attacks, or finding patterns without labeled data, think unsupervised learning. Anomaly detection deserves its own deep dive because it's one of the most tested topics within ML security. Let me explain why. Anomaly detection finds threats that signature-based systems completely miss. Traditional security tools like antivirus and IDS rely on known signatures, patterns of known attacks. But what about a zero-day exploit that nobody's seen before? Or an insider threat where a trusted employee slowly exfiltrates data? Or an advanced persistent threat that uses legitimate tools to move laterally? Anomaly detection catches these by identifying deviations from baseline behavior, not by matching known patterns. A key concept you'll see on the exam is UEBA, User Entity Behavior Analytics. UEBA builds behavioral baselines for users and devices over time, then flags deviations. It knows what's normal for each user, when they log in, what they access, how much data they typically transfer, and alerts when behavior deviates significantly. Let me walk through 4 common exam scenarios. First, impossible travel. A user logs in from New York and then from London 30 minutes later. That's physically impossible and gets flagged as a geo-anomaly. Second, a server suddenly sends 10 times its normal outbound data at 2 a.m. That volume anomaly could indicate data exfiltration. Third, an employee starts accessing files they've never touched before, an access pattern anomaly that might indicate an insider threat or a compromised account. Fourth, a new process appears on a production server that isn't in the baseline, a process anomaly that could indicate malware or a backdoor. The exam loves these scenario-based questions. When you see descriptions of baseline deviations, think anomaly detection. When you see unknown or novel threats, think unsupervised learning. Reinforcement learning completes our trio of ML paradigms. The core loop is, agent takes an action in an environment, receives a state update and a reward or penalty, and uses that feedback to learn a better strategy over time. Unlike supervised learning, there's no labeled dataset. The agent learns through interaction. Looking at the RL loop on the left, the agent observes the current state of the environment, takes an action, and the environment responds with a new state and a reward signal. The agent's goal is to maximize cumulative reward over time. It's essentially learning a strategy through trial and error. On the right, the security applications. First, adaptive firewall rules. An RL agent can learn optimal firewall policies by testing different rule configurations against live traffic patterns, getting rewarded when it blocks attacks, and penalized when it blocks legitimate traffic or lets attacks through. Second, automated penetration testing. This is a fascinating application where an RL agent explores attack paths against a target system, learning which exploits are most effective. This helps security teams discover vulnerabilities before real attackers do. Third, dynamic access control. The agent adjusts access policies in real time based on observed risk signals. If a user's behavior becomes suspicious, the agent can automatically tighten their access without human intervention. Fourth, intrusion response. Learning the optimal response action for different threat types. Should it block the IP, throttle the connection, isolate the host, or alert the analyst? The RL agent learns the best response by observing outcomes over time. For the exam, reinforcement learning questions are less common than supervised and unsupervised, but when they appear, they typically describe adaptive systems that learn from feedback to optimize security decisions over time. This comparison table is your exam cheat sheet for choosing the right paradigm. Let me highlight the most important distinctions. Data required. Supervised needs labeled data. Unsupervised works with unlabeled data, and reinforcement needs an environment with a reward signal. This is the fastest way to identify the paradigm on the exam. Strengths and weaknesses are where the exam gets tricky. Supervised learning gives you high accuracy on known threats and interpretable results, but it cannot detect unknown threats and requires expensive labeling effort. Unsupervised learning excels at detecting novel and unknown threats, but typically produces higher false positive rates and can be harder to tune. Reinforcement learning adapts to changing environments, but is complex to implement and slow to converge. The best for row is critical. When the scenario involves classifying into known categories, it's supervised. When it involves detecting anomalies or unknown threats, it's unsupervised. When it involves adapting policies or automated decision-making, it's reinforcement. At the bottom, I've given you a simple decision rule. If the question mentions labeled data and known categories, choose supervised. If it mentions no labels and finding hidden patterns, choose unsupervised. If it mentions a feedback loop and optimization over time, choose reinforcement. This decision rule alone will help you answer many exam questions correctly. Before we wrap up, let's preview the attacks that target ML models. This is a preview because we'll cover them in exhaustive detail in sections 4 through 7 as part of Domain 2, which is 40% of the exam. But it's important to understand these now so you can see how the paradigms we just learned about can be exploited. Data poisoning is when an attacker corrupts the training data to manipulate model behavior. For example, injecting malicious files that are labeled as benign into a training dataset. When the model trains on this poisoned data, it learns to classify those malicious files as safe. This affects both supervised learning, where labels can be flipped, and unsupervised learning, where injected data can shift cluster boundaries. Adversarial evasion is crafting inputs specifically designed to fool a trained model. By making small, carefully calculated perturbations to an input, changes often invisible to humans, an attacker can cause the model to misclassify. For example, slightly modifying a malware binary so it gets classified as benign. This primarily targets supervised models. Model inversion extracts sensitive information from the model itself. By carefully querying the model and analyzing its predictions, an attacker can reconstruct aspects of the training data. If the model was trained on sensitive data, this could leak private information. Model stealing involves querying a model's API to build a functional copy. The attacker sends many inputs, collects the outputs, and trains their own model that mimics the original. This is a form of intellectual property theft. All of these attacks are heavily tested on the SecAI Plus exam. For now, just be aware they exist and understand which paradigms they target. We'll dive deep into attack techniques and compensating controls in Domain 2. Excellent work completing Lecture 2.2. This was a dense lecture with a lot of critical exam material. Let me summarize what you've mastered. You can now explain all three megaleaders paradigms and their core mechanisms. You can distinguish between classification and regression tasks in supervised learning. You understand anomaly detection and UEBA, which are the most heavily tested unsupervised techniques. You can name key algorithms for each paradigm: random forest and SVM for supervised, isolation forest and k-means for unsupervised, Q-learning, and DQN for reinforcement. You have a clear decision rule. Labeled data means supervised, finding patterns means unsupervised, and feedback loops mean reinforcement. And you've previewed the 4 major attacks on ML models. The key evaluation metrics, accuracy, precision, recall, and F1 score, are particularly important. The exam loves to test whether you understand the trade-off between precision and recall in security contexts. Remember, high precision means fewer false alarms, high recall means fewer missed threats, and in most security applications, missing a real threat, low recall, is worse than generating a false alarm, low precision. Coming up in Lecture 2.3, we'll dive into deep learning and neural networks for security. We'll explore CNNs, RNNs, and transformers in detail, understand how attention mechanisms work, and see how these architectures power the most advanced security tools available today. See you in the next lecture. Welcome to Lecture 2.3, Deep Learning and Neural Networks for Security. In our previous lectures, we established the AI hierarchy and covered the 3 megaleaders paradigms. Now we're going deeper into the architecture that powers the most advanced AI security tools today. Deep learning is a subset of machine learning that uses neural networks with multiple layers. What makes it special is its ability to automatically extract features from raw data. You don't need to manually engineer features like you do with traditional ML. This is a game changer for cybersecurity, because threats are constantly evolving, and manual feature engineering can't keep pace. By the end of this lecture, you'll understand how neural networks process data through layers. Know the 3 key architectures tested on the exam: CNNs, RNNs, and transformers. Understand the attention mechanism that powers modern NLP security tools, and be able to match each architecture to its security use cases. Let's dive in. Before we dive into specific architectures, let's understand how neural networks work at a fundamental level. Look at the diagram on the left. A neural network consists of layers of interconnected processing units called neurons. Data flows from left to right. The input layer receives raw data. It passes through multiple hidden layers that progressively extract more complex features, and the output layer produces the final prediction or classification. On the right, let me walk through the key concepts you need to know. Neurons are the basic processing units. Each neuron receives inputs, multiplies them by weights, sums them up, and passes the result through an activation function. Weights are the parameters the network learns during training. They determine how much importance to give each input signal. Layers are what make it deep. The more hidden layers, the deeper the network, and the more complex patterns it can learn. Activation functions like ReLU and sigmoid introduce nonlinearity, which is crucial because without them, the network could only learn linear relationships, and real-world security data is highly nonlinear. Backpropagation is the training algorithm that adjusts weights by calculating how much each weight contributed to the error, then propagating corrections backward through the network. And the loss function measures how wrong the predictions are. Training is essentially the process of minimizing this loss. For the exam, you don't need to code neural networks, but you need to understand these concepts, and especially the key distinction from Lecture 2.1. Deep learning automatically extracts features through its layers, unlike traditional ML, which requires manual feature engineering. Convolutional neural networks, or CNNs, are designed to process grid-like data, most commonly images. The key innovation is the convolutional filter, a small matrix that slides across the input detecting local patterns like edges, textures, and shapes. The CNN pipeline has 4 stages. First, convolution filters slide across the input detecting local patterns. In malware analysis, these filters might detect specific byte sequences or structural patterns. Second, pooling. This reduces the spatial dimensions while preserving the most important features, making the network more efficient and reducing overfitting. Third, the feature maps are flattened into a vector and fed through dense, fully connected layers for final processing. Fourth, the output layer produces the prediction. Now, the security applications. Visual malware analysis is fascinating. Researchers convert malware binaries into grayscale images by treating byte values as pixel intensities. Different malware families produce visually distinct patterns, and CNNs can classify them with high accuracy. This works because malware from the same family shares similar code structure. Network traffic classification converts packet data into image-like representations, then uses CNNs to classify traffic flows as normal, malicious, or specific attack types. Image-based CAPTCHA solving is a threat vector. Attackers train CNNs to bypass visual CAPTCHAs that protect web applications. And STEG analysis uses CNNs to detect hidden data embedded in images by analyzing subtle pixel-level anomalies invisible to the human eye. For the exam, remember, CNNs are for spatial patterns in grid-like data. If the question mentions images, visual analysis, or spatial features, think CNNs. Recurrent neural networks are designed for sequential data, where the order of inputs matters. Unlike regular feed-forward networks where each input is processed independently, RNNs maintain a hidden state, essentially a memory, that carries information from previous time steps to the current one. The key insight is memory. RNNs